Here today to present information design for differential privacy is joint work with my colleague at UGA, Ian Schmutte. All right, so to motivate this talk, suppose you're Apple. And every day you collect information about what millions of people do with their devices, what apps they use, what websites they visit, where they go, their location data. And for whatever reason, you don't want the database you're building to expose too much information about these sensitive activities. Maybe you think that by offering a privacy guarantee that might make your product more attractive to consumers. Maybe you think that if this database you have was ever leaked and you didn't take explicit privacy precautions when you were building it, it might create a huge legal or PR issue for you. Alternatively, suppose that you're the US Census Bureau. You collect information on the characteristics of millions of people and businesses, sensitive characteristics like income, race, who you live with. And you're required by law to prevent what you publish about this data from providing too much information about any single individual. So the solution that a lot of organizations have settled on is to adopt mechanisms for publishing information that satisfy a criterion from computer science called differential privacy. And what differential privacy does is it requires that given any data you might collect, the output that the mechanism provides or publishes is randomized. And in particular, it's randomized in such a way that limits the amount that a change in any individual's data can change the probability of any given output. And one of the reasons that this has become so popular is that this criterion offers an explicit formal guarantee of privacy in contrast to the more ad hoc measures that have been traditionally used by these data publishers. So to make this concrete, I want to describe what the differential privacy criterion says in general. And in the basic environment where differential privacy applies, we've got a database that I'll call theta, composed of a bunch of records, theta n for individuals. Or to use more familiar terminology for economists, you can think of the individuals' records as being their types, and the database as being the type profile. And the thing that differential privacy applies to is a publication mechanism, a map from the set of possible databases to distributions over some set of outputs, or what an economist might call a signal. And what differential privacy is going to say is that a change in a single record, so a single individual's type, can't change the log probability of any given output by more than this parameter epsilon, which is sometimes called the privacy loss budget. And when it satisfies this, we say that it's epsilon differentially private. Now, importantly, this criterion requires a designer to commit to the mechanism without accessing the data, because we're comparing the probability of a given output across counterfactual databases. So there's no way I can prove that the probability of an output would be within, or the log probability of this output would be within epsilon under this counterfactual database if I could have chosen a different mechanism had the database been different. So I'm implicitly required to commit to a data publication mechanism. But there are lots of data publication mechanisms that satisfy this criterion. Which one should a data provider use? Well, this is an applied information design problem. The data provider is choosing a signal under commitment. And in this paper, we're going to talk about the solution to that problem. But in order to meaningfully do that, we've got to be a little bit more specific about the kinds of data the designer is gathering and what he hopes to achieve by publishing it. So the kind of data we're going to consider is pretty simple. We're going to consider data composed of records about whether respondents have some sensitive characteristic. Maybe that's whether they left their house today. Maybe that's whether they have income over $100,000. Maybe it's whether they're African American. Maybe it's whether they tested positive for COVID. And if they have this characteristic, we'll say that their type is 1. If not, we'll say it's 0. And there's n of these respondents, big N, in the database. Now, importantly, we're going to assume that the respondents in the data are ex-ante anonymous. So before we see the data, we don't think it's any more likely that these 50 people have COVID than these 50 people have COVID. So our prior over type profiles is symmetric. Now the data provider wants to publish information in a way that maximizes the payoffs of decision makers or data users who are going to use the output of the mechanism to make a decision. And when they do that, the decision makers, they do not care about the type of any single individual. They only care about how many people are type 1, how many people have this characteristic, what we're going to call the state. And for a type profile theta, we're going to denote the state for that type profile omega theta. Now, we've got n respondents, so our set of states is going to be the integers from 0 through n. You can have from 0 to n people be type 1 in this sample. And our prior over type profiles is naturally going to induce a prior over states, mu naught. Now, decision makers' payoffs depend on their own action and on the state. Importantly, they do not depend on the actions of other decision makers. So these decision makers are not playing a game. They have independent decision problems. Now, to make this a little bit more concrete, I want to consider an example. Suppose a university has tested 2 random members of its economics department for COVID. So the number of respondents, or n, is 2. And their types represent their test results. So they're type 1 if they have COVID, and 0 if they don't. And the university wants to disclose information about the positivity rate to other faculty so they can make better decisions about whether to wear an N95 or how much to interact with their colleagues. But they're concerned that by doing so, they could compromise the privacy of the faculty who have been tested. So they've given those faculty a guarantee that anything they publish about their test results is going to be epsilon differentially private with an epsilon of 1. Now, since the department's faculty work in the same building, the surveillance test results are going to be correlated. In some sense, that's the whole reason we care about the surveillance test results. And for simplicity, suppose that they're correlated in such a way that the prior probability of any state, so 0 people testing positive, 1 person testing positive, or 2 people testing positive, is the same. They're all 1/3. And for simplicity, let's say there's only one decision maker, and this decision maker is deciding whether to go to lunch with some other colleagues, not the ones who have been tested, an action I'll call X, or stay home, an action I'll call Z. And if he stays home, he's going to get the same payoff no matter what. But if he goes to lunch, the payoff he expects to get is going to be decreasing in how many people tested positive. The more people tested positive, the more likely it is that someone in his lunch group is going to have COVID and give it to him. Now, I'll return to this example throughout the talk to illustrate our 2 main results. And our first main result shows how to use tools from the information design literature, so representing the signal as a distribution of posterior beliefs, and then concavifying a value function over those beliefs to characterize the problem. And in particular, we'll show that the problem is going to simplify to one of choosing a distribution of posterior beliefs over states rather than over type profiles, subject to a constraint on the posteriors that we can induce that represents the differential privacy requirement. And the nature of that constraint is going to put additional structure on the problem solution relative to a standard information design problem. Now, in a large class of settings, we'll be able to go further. So in settings where the agents that are going to use the data have supermodular decision problems, so there's a complementarity between actions and states, we're going to show that a simple mechanism which is simple to describe, is always going to be optimal across an entire class of settings. And the key insight that lets us do this is a novel comparison of experiments results that ranks information structures according to their usefulness to agents with supermodular decision problems. Okay, so let's get started. So the first thing we want to do is simplify the problem faced by the designer. Now, since the decision makers, they only care about the type profile through the state. The designer only cares about the type profile through its impact on the decision makers. We might think, instead of thinking about signals about the entire type profile, we can restrict ourselves to thinking about signals of just the state that only depend on the state, what the CS literature would call oblivious mechanisms, here for a count query. And this turns out to be right. So if we have a differentially private mechanism, we can construct a new one that's oblivious, so it only depends on the state, not necessarily on the whole type profile, induces the same distribution of posterior beliefs about the state, which is what matters for the decision makers, and it's still differentially private at the same level, for the same epsilon. Now, the form of this new mechanism is pinned down by Bayes' rule. That's pretty simple. What's a little bit more tricky is to show that it's going to inherit differential privacy from the old mechanism that's not necessarily oblivious. And that's going to follow from the symmetry of the prior. So the fact that we said that we assumed that these respondents were ex ante anonymous. So we can restrict attention to oblivious mechanisms. That makes our designer's problem a lot easier. We don't have to mess around with type profiles, just with states. And when we do that, we can simplify our differential privacy criterion. Instead of bounding the log likelihood ratio of type profiles that differ in one entry, we can bound the log likelihood ratio of states that are adjacent. Why? Because when we change one entry in our database, we're either changing a 0 or a 1 to a 1 or vice versa. So we're changing the total number of people who have type 1 by 1. So we're changing the state by 1. And in fact, we can rewrite this condition as a condition not on the signal, but on the posterior beliefs induced by the signal about the state. And to see this, note that Bayes' rule implies that the posterior odds of one state omega prime against another one omega is just the prior odds times the likelihood ratio for the output that we saw in order to update to this posterior. So we can say that an oblivious mechanism is differentially private exactly when it induces posteriors such that for every pair of adjacent states, the distance between their log odds under the posterior and under the prior is less than epsilon. And we'll call the set of posteriors that satisfy this condition the set of epsilon differentially private posteriors. And what does this look like? Well, in our COVID example with 3 states, uniform prior and epsilon of 1, this set of differentially private posteriors looks like this diamond here. So differential privacy amounts to saying we can't induce posteriors anywhere on the simplex, only within this diamond in this example. More generally, our set of differentially private posteriors is always going to be a closed convex polyhedron, which will be important in a moment. So since differential privacy amounts to the requirement that we only induce posteriors in this set, well, we can write the designer's problem as a standard information design problem, where we're choosing a distribution of posteriors to maximize the expectation of a value function, which here is just the sum of decision makers' interim payoffs, subject to a constraint that the expected posterior is a prior, the Bayes plausibility constraint. But unlike in a standard problem, we have to restrict ourselves to distributions on the set of differentially private posteriors, not on the entire simplex. Now note that because the designer's incentives are aligned, with the decision makers, and our constraint set is closed and convex, Blackwell's theorem says, well, we can restrict attention to distributions on the extreme points of the constraint set, so the vertices of the polyhedron. And furthermore, note that if we replace the designer's value function with its restriction to the constraint set, well, now this looks just like a normal information design problem, a standard information design problem, and so that means we can apply standard results to it. And that's what we do in our first theorem, which I'll illustrate in the context of our COVID example. So we'll start with our restricted value function. The first part of our first theorem says that the maximized value of the designer's problem is the concavification of this restricted value function, so the smallest concave function that lies everywhere above it, evaluated at the prior, standard information design result. Second result says that the problem has a solution that induces a distribution on the extreme points of our constraint set, and that distribution is uniquely pinned down by the posteriors in its support. Here, those are the posteriors at the left, right, and top corners of the constraint set. And it turns out that's the distribution in this example induced by a canonical mechanism from the CS literature called the geometric mechanism, which is generated by taking two-sided geometrically distributed noise, adding it to the true state, and publishing the result. Now, there's a key contribution in the computer science literature that doesn't set up an information design problem, but does show that the geometric mechanism is optimal for a specific kind of decision maker problem, where decision makers are trying to match their action to the state to minimize a symmetric loss function. Our COVID example isn't in this class, though. So it seems like there must be something not captured in this match the state functional form that's driving both our example and their result. And there is. The two key things that we need are in both our example and in this match the state setting, higher states and higher actions are always going to lead to higher actions. So in the COVID example, higher states led to more precaution. In match the state, higher states always lead to higher actions. Second, in both of these, we can order all of the actions from lowest to highest. So formally, our second main theorem says that if each decision maker's actions are real numbers, or equivalently, they're totally ordered, and each decision maker's payoffs are supermodular, then the geometric mechanism is always going to be optimal. All right, I'll stop there.
All right, yeah. Well, thank you very much for the talk. So yeah, let's maybe once again take 2 questions right now, and then move on to the next speaker. So yeah, does anyone have any question here?
Yeah.
Using types and counts, this is very specific. Is it possible to generalize it to something like, I don't know, that you don't count number of records, but maybe do mean on them or average or something like that?
Yes, the big difference if you're interested in say the average income, right, in a sample. The big difference that you're going to run into there is then its oblivious mechanisms are no longer going to be without loss. So here it was without loss to just think about signals that only depended on the true value of the statistic you were interested in. Not going to be true more generally. You can actually do better than that, which that's something that one of the referees asked us too. And yeah. All right.
Yeah, you wrote this at the census. I don't know if I saw this in the working paper version.
So my colleague at Georgia, so my co-author on this, he has a census affiliation as well, and he did have it put out through the census working paper series, yeah.
Can you say something on whether something of these insights scale to the problem of the census?
So one of the issues, so that's a good question. So as I said, so a lot of the census problems are things like what you mentioned, where you're interested in publishing a mean rather than just, a count. So in that sense, no, although some of our, we think that there's a version of this theorem, theorem 2, that's going to be applicable there, but it's just not going to be for the geometric or Laplace mechanism. As far as, for categorical data, we do think that it's potentially applicable to Census Bureau publishing categorical data. So kind of what you can think of this as saying for practical purposes is like, if you're publishing, these counts of categorical data within like a census block, and some environments are naturally going to have complementarity with decision maker actions. Their geometric mechanism is going to be optimal. Outside of that, that's not necessarily going to be true. So we have a counterexample where that's not going to be optimal in the paper. So there, you might want to think about using our more general characterization in the first theorem.
All right, yeah, thanks a lot. Thanks again for the great talk. And yeah, let's move on to the next speaker. Fine. Yeah.